Hi, welcome back to this course on computational thermodynamics and kinetics of materials. Today we'll continue with thermodynamics of materials, chemical potential, activity and solutions thermodynamics we will see in this class. These are the contents. Chemical potential we have seen in the last class. We'll see more about that in this class and see how Gibbs energy versus composition diagrams, one of the most important ideas for this entire course, GX plots. We'll see how that comes from chemical potential. And chemical potential, we will see that more mathematically using how it applies to open systems. And then concepts based on understanding what is vapor pressure, ideal mixing, non-ideal mixing, the thermodynamic activity, partial molar Gibbs energies, chemical potential, all these things through the lens of vapor pressure, and how chemical potential and activity are related and how phase equilibria is ultimately understood based on these ideas. In the last class, we saw about the mechanical mixture properties. So if we make two elements A and B mix or react with each other, this is before the mixing, pure A and pure B, and the mechanical mixture Gibbs energy or the initial state Gibbs energy, we call this GI or G reference, XAGA plus XBGB. If we mark it in this Gibbs energy versus composition plot, we'll call this point as Gibbs energy of pure A, this is Gibbs energy of pure B. And for a chosen composition, let's say 0.5 mole fraction of B, we are going to have the reference state Gibbs energy lying on this line. This is the rule of mixture line. So this is a reference Gibbs energy. Since G and GB values have a reference state, for example HSCR, meaning the enthalpy at 298 is 0. In that way, the mechanical mixture Gibbs energy GI is called as a reference state Gibbs energy. It's nothing new, we have seen this in the last class. Now once we mix this, then what happens? The Gibbs energy of pure A and pure B will be different now in this solution, right, compared to its standard state. So the Gibbs energy of A changes to a new value, and this is the Gibbs energy of A in the solution. We call it chemical potential of A. Similarly, Gibbs energy of B changes to another value. This is the chemical potential of B in the solution. Therefore, for this composition, the Gibbs energy of the solution will be lying in this line here. This is the Gibbs energy of solution, which is nothing but a rule of mixture of this mu A and mu B based on the mole fraction. So that is G of phi, the phase phi's composition, phi is the solution's name now, XA mu A plus XB mu B. Right. So this is the Gibbs energy of the solution. How is it different from this mechanical mixture Gibbs energy? This delta G mix has to be added. So we can write it mathematically like this. Now what if we change the composition? In this case, you can see amount of A and B is not same. XA and XB are now different. They are not 0.5 anymore. Now for that composition, how do we understand this chemical potential? Now this is not at the center, it is somewhere in the left hand side now. A rich composition. There, if the mechanical mixture Gibbs energy is going to lie here, the reference state Gibbs energy. From there, how the Gibbs energy of pure element A will change. The Gibbs energy of A will go down to this value, not as high as the previous case. This is the new chemical potential for A. Similarly, for the B, the chemical potential will be far lower, because for this total overall composition, this is how the chemical potentials will be. So this is where it is going to lie. So this is the Gibbs energy of solution. Right. So this is the del G mix now. So what has happened compared to this composition? Definitely mu A has increased from a point like this to here, and mu B has decreased from a point like this to here. So this was the Gibbs energy then. Now what happens if we keep changing the compositions? We went left here from this point. If we go further left or if we go right, what happens? So if we consider from left to right, gradually you will see that the total Gibbs energy of the solution follows some kind of a curve. Right? So let us look at that graphically. And that's what GX diagram will be. Let's see that. You start with pure A, here it is completely pure A, and this is going to gradually become B, pure B. Okay, the number of orange atoms are going to increase here as we go from left to right. And then what happens to Gibbs energy at each of that composition? Total Gibbs energy, this G5, we are going to track that. It's going to become something like this. You can see. Okay, so for as the composition changes, you can see the Gibbs energy values change, and here the atomistic picture is also given for your assistance. So this is how the Gibbs energy of solution will change, and you know how it comes. Basically, chemical potential of each of the element is different in different overall compositions. So this is Gibbs energy versus composition diagram, or GX diagram, or GX plots. We will be using it almost all along the course. A related idea is this Gibbs-Duhem relation. If we take this composition, this is the chemical potentials average, weighted average, and that is going to be the new Gibbs energy. Now, if the overall composition changes, we get another value as the new Gibbs energy. If that is so, then the chemical potentials change like this. The chemical potential of A increased from this value to this value. Chemical potential of B decreased from this value to this value. And if you take the original composition, this is the XA quantity, this entire length is XA and this entire length is XB, right? So if you take these values, XA, multiply that with d mu A, and take XB and multiply that with d mu B, right? So XA d mu A plus XB d mu B, it's more like the seesaw, right? So this is a quite important formula. What happens when the overall composition changes? As XB increases, XA decreases. That is obvious from XA plus XB equals 1. And the chemical potential of A and B changes, but the change in only one is independent. The other is dependent on that. If mu A decreases, mu B increases accordingly following this formula. Okay, and this relation can be generalized like this. Summation over I, xi d mu I is equal to 0. So this is called as Gibbs-Duhem relation. This is quite useful to know state properties. When we know state property change of one of the elements, from that we can get the state property change of the other element. So in that way, this becomes a quite useful relation. Right now, we will not bother too much about this, since this is very much understandable just after understanding the chemical potential. I have put it here. When we use this kind of relation later, that time we will treat this in a more rigorous manner. Right now, we will understand chemical potential in more detail. Chemical potential becomes actually very important in open systems, where we will consider first an unary system. If it is a closed system, we know Gibbs energy is a function of pressure and temperature, and dG equals VdP minus SdT. We got this from the combined first and second law using Legendre transformation, if you remember. So this particular equation has change in P and change in T will give change in G, right? Now this is true for closed system. What if we have an open system? Okay. So now this is an open system. Let's say this is all component A, some gas A, let's say, and this entire thing is at constant pressure and temperature. Okay, you can see that on the top there is some mass kept, and this is at constant pressure. The temperature is maintained constant. Now if we add one atom of A to it, what happens? Okay, since the pressure and temperature is constant, will you say Gibbs energy will not change according to this equation? Pressure is constant, temperature is constant. Will dG be constant? dG be 0? Answer is no, because Gibbs energy is an extensive quantity. Obviously, when one more number of atoms are added, Gibbs energy is going to go up. Okay, so in open systems, Gibbs energy is function of pressure, temperature, and also number of atoms. Okay, number of atoms are of A in this case. So Gibbs energy change will be proportional to number of atoms of A change. So dG equal to, if we change this proportionality to equal, then we get a proportionality constant here, that is mu A now. If we add more atom, then the system size is going to increase. Then we can say for each addition of atom, what is the change in Gibbs energy at constant pressure and temperature? That is called as chemical potential. So the same chemical potential, we are looking at it in a slightly different manner using this analogy. So I hope this is intuitive to understand. So mu A is dG by dNA at constant pressure and temperature. So if we generalize this for any component I, change in G per atom of component I at constant pressure and temperature is chemical potential of I. Or more practically, we will be using this mu A as a function of number of moles of A rather than number of atoms of A. So this is more useful. So therefore mu I we can write as change in Gibbs energy per mole of component I at constant pressure and temperature. So this is all about unary system chemical potential. More important and practical application of this will be in the multi-component system. So let's start with the binary systems. If two gases are there and pure A and pure B, and if you remove the partition between them, they are going to get mixed. So this is, let's say, some ideal gases mixing kind of thing. So in this case, will the chemical potential change? As elements A and B mix, the Gibbs energy of each element changes, right? So therefore, chemical potential of A is the change in Gibbs energy per number of moles of A at constant pressure, temperature, and number of moles of B. We have to keep the amount of other element constant, only then we can talk about adding only A and seeing the Gibbs energy change. So mu A is Gibbs energy change per mole of A when the number of moles of B and pressure and temperature are constant. Similarly, we can have chemical potential of B as Gibbs energy change of B with respect to the change in number of moles of atoms of B when number of moles of atoms of A and pressure and temperature are constant. Total change in Gibbs energy of the two component system at constant pressure and temperature is nothing but this. Gibbs energy change is chemical potential of A multiplied by the change in number of moles of A. If this is the change per mole of A, then what is the actual change in the number of moles of A? That will be multiplied with that. Similarly for B we do that and sum both the things, we get the Gibbs energy change for the entire system. Now generalizing this for a multi-component system, we can write with this subscript notation summation over I mu I dNi, any number of elements. Okay, if this is true for constant pressure and temperature case, if we want to change pressure and temperature also, when P and T change, what happens? We know what happens. dG is VdP minus SdT. We already know this. This is how the dependence of G is with respect to P and T. And to that, we have to add this new guy also, which is because of this multi-component system, where mu I dNi comes. So this is the change in Gibbs energy of multi-component system, and this is what we have to track in order to know whether the multi-component system will change to any other state, or will it be stable, will there be phase transformation, will there be reaction. All those questions will be answered by tracking this change in Gibbs energy like this. So this is a quite comprehensive equation for G. Gibbs created this modern science of physical chemistry. Imagine all the way from the engines to their efficiency and the entropy coming out of that. All those ideas developed for a different domain of science and engineering is applied by Gibbs to materials, the chemistry of materials. Such is the contribution of Gibbs. Right, this is the summary of what you have seen till now. Now, all this may sound little mathematical to many of you. The same ideas we will understand through something called vapor pressure. That will be more intuitive to understand. Let us see that. If you consider the case of entropy of mixing that we saw in the last class, where mixing of ideal gases happen, when they are separated and the partition is removed, they will end up in this final state. So obviously the natural process goes in this direction, and we derived the configurational entropy of mixing, and we brought this formula out from the Boltzmann equation, and this is going to be the Gibbs energy change of any ideal mix minus temperature into delta S mix, because there will be no delta H mix. So in that way, the Gibbs energy change depends only on the entropy change. That's what drives this mixing. So why in nature two gases mix? It's because of Gibbs energy going down. And why Gibbs energy is going down? Because the entropy increases. This idea is going to help us understand more ideas based on vapor pressure. Let us see what is that. Consider a solid, a pure A. All about 30 atoms are there here. All are A. And if you consider a small contained space above that, and imagine all types of gas atoms are there, the atmosphere is there on top of that. So that will be exerting a pressure of 1 atmosphere. And in that, there will be a part of that gas that is from this same A atoms. So you may ask why when pure A is solid at this temperature, why should there be gas of A? Some of you may have this doubt. Actually, at any temperature, there will be a small amount of gas atoms of the same solid in equilibrium with the solid. And that number actually increases with respect to the temperature. Okay. On top of liquid also, there will be some gas atoms. Okay. At boiling point, the amount of vapor, the vapor pressure is equal to the atmospheric pressure. Okay. There will be a pressure exerted by this gas on the solid. So here in this case, the pressure that is exerted by only A atoms is called as partial pressure of A, and that amount of gas is in equilibrium with the solid. Okay. So this is called as P, standard A, partial pressure of A, or standard vapor pressure of A. So because this is the standard state of A, if A is in its crystal structure at this temperature at 1 atmosphere pressure, we call it standard state of A. To that A, how many gas atoms are, what is the kind of pressure exerted by the gas atoms when the A is in its standard state? That is called as standard vapor pressure of A. Similarly, for B, let's say there is some B atoms in vapor state. Obviously, the numbers will be different here, 6 atoms, here 4 atoms, because these are two different elements. They will have two different standard vapor pressure. So for B, it is this. Now, what if we form a solution now? A and B, let's say, they have nicely mixed and formed a solution in atomistic scale. And if it is an ideal mixing, meaning A and B do not interact, then the enthalpy of mixing will be 0. We have seen this idea already. The mole fraction here, Xa is equal to 1, all are A atoms. Here the mole fraction of B, Xb equals 1, all are B atoms. And here, since in this solution A and B are equal, 30 atoms of A and 30 atoms of B, Xa and Xb will be 0.5. Now, how many atoms of A and B will be there in the vapor? You see, A is now 3 and B are 2. There are 6 atoms here, but only 3 here. There are 4 atoms here, but only 2 orange atoms come here. Now, why has this happened? It's because there is a mixing in the solid state, right? A and B, of course, do not bother about each other. We say there is no interaction. So, A has same bond energy to the neighbor, whether the neighbor is A or B. If that is the case, what stops A from going from the solid state to liquid state, solid state to vapor state, as if it was pure? Okay. Now, problem here is, since A and B are mixed in the solid state, there is a kind of entropy of mixing, that is the one which drives this mixing itself, because we are putting the word ideal mixing also, right? So there is a complete dominance of entropy here, and all the atoms mix with each other in the solid state well. Because of this, the atom escaping from the solid to vapor are going to go down. There is a tendency to be mixed in the solid state because of entropy of mixing. When we see in the next slide, you will see that the enthalpy of mixing, if it is negative, let's say, obviously in the solid state there is more tendency for the atoms to be mixed, right? A and B atoms, let's say, they like each other, so they would like to be bonded in the solid state. In that case, you will obviously expect less number of atoms to come to vapor state. But in this case also, in ideal case also, there is a tendency for the atoms to mix in the solid state because of entropy of mixing. Therefore, the number of atoms coming to vapor state will be lesser. How much lesser? depends on the mole fraction of A and B in the solid state. You can see 6 has become 3 blue atoms, 4 have become 2 the orange atoms. Basically, the vapor pressure of A here is multiplied by this mole fraction. Okay, so if we want to know partial pressure of A on top of solution phi, this is the solution, okay, not standard state of A anymore. What do? Take the standard vapor pressure of A, multiply that with 0.5, you get PA phi. Okay. Similarly, for PB phi, take the partial pressure of standard vapor pressure of B, multiply that with 0.5, you get this. What we are doing is taking the mole fraction of A and multiplying that with the standard vapor pressure to get the actual vapor pressure on top of ideal solid solution. Okay, so in this case, ideal solutions, this will be the behavior. The solution's partial vapor pressure of any element will be mole fraction of that element multiplied by the standard vapor pressure of that element. Right, now let's see the non-ideal case. So this solution has attraction in the solid state. A and B like to be together, more A and B bonds will be there. Therefore, this is a non-ideal mixing. Delta H is less than 0 in this case. If that is so, then number of atoms of A and B in vapor will be far lesser. And if you see PA phi and PB phi, they will be less than this XA PA standard and XB PB standard. This is because in solid state atoms would like to be mixed more, A and B bonds will be more. That's the reason why we see less number of atoms coming to the vapor state. The opposite to that happens in this case where more number of A and B atoms are there compared to their standard state. Why this happens? This is again non-ideal mixing, but this PA standard and PE standard, PA phi and PB phi will be more than the mole fraction multiplied by the standard vapor pressure. This happens because of a repulsion in the solid state. So the A atom, B atom, they do not want to be neighbors like this. So rather than being neighbors with the atoms which they do not like, they better go into vapor state. That's the reason why you find more number of atoms coming to vapor state. That is the repulsion in solid state. Delta H is greater than 0 in this case. Now, through this lens, we will understand this idea called thermodynamic activity. It's a very beautiful idea. Let's think about the ideal case once again. Here we have this pressure of A over the solid solution phi, which is lesser than pressure of A over the standard state. So in this case, what has happened is the pure A, when it has become a solution in the solid state, this solid state behavior of A is captured in the vapor of A. If you see the vapor of A, the amount has decreased here according to this formula, the mole fraction multiplied by PA standard. This decrease in vapor pressure is an indicator of what happens to the A in the solid compared to the pure form of A. So this ratio then gives us a hint about the solid state behavior. Partial pressure of A over phi and the standard partial pressure of A. So this can be called as activity of A in phi. This small a here, that is the notation used for activity. So activity of element A in solution phi. This is how it is indicated. Activity is in this case will be equal to this XA PA standard by PA standard, which will be XA, mole fraction of A. So mole fraction of A is the activity. It means that compared to its pure form, here activity of A in A, which is just PA standard by PA standard, is equal to 1. This is why we say activity of pure components is 1. So compared to this, here it has become a fraction. From 1 it has become a fraction. It means that the activity of A is now reduced compared to its pure form when it goes to the solution form. So in the pure form, the activity is 1, in the solution form it is just a fraction. Similarly, when the solution is not ideal and when there is a negative enthalpy of mixing, we will see that the mole fraction of A is higher than the activity of A, meaning more atoms would like to be here in the solid, reducing the activity of A, meaning A is not very active to come to the vapor state. It is less active, meaning it is more stable. When delta H mix is positive, Obviously, there is more number of atoms in the vapor state, making the activity of A higher than its mole fraction. Now, activity being so intuitive, can it help understand phase equilibrium? Let's consider this phase phi. On top of that, we have certain amount of Pa phi and Pb phi. Now, if there is another phase, let's call it alpha. It has a different crystal structure, different chemistry, chemical composition compared to the phi. Here we have Pa alpha and Pb alpha, same as Pa phi and Pb phi, right? So Pa alpha here is equal to Pa phi here, and Pb alpha here is equal to Pb phi here. If that is the case, only then these two phases can stay in equilibrium. If two phases are in equilibrium, activity of each element must be same in both the phases. So if you calculate activity of A on this side, Pa alpha divided by Pa standard and Pa phi divided by Pa standard, you are going to get the same value. Similarly, for Pb alpha and Pb phi also you will get the same value. Therefore, this is true, activity of each element must be same in both the phases. Otherwise, movement of atoms is possible between the phases to attain equilibrium. We are going to see more about this otherwise part. Right now we are focusing mostly on equilibrium part. So therefore, this is true. The second sentence we'll see more about that in future when we see the diffusion and stuff like that. Right. We can summarize this about the activity and phase equilibria. Activity of an element A in two different phases should be same for these phases to be in equilibrium, alpha and phi. So phases in equilibrium, activity of an element must be same across the phases. So this is about activity, but why we considered this vapor to understand the solid? That would have been obvious by now, but by next couple of slides it will become more obvious. Delta G of an ideal gas during a pressure change. If we consider this, it is going to throw some light. Now dG is VdP minus SdT. Gibbs energy change. This is an ideal gas we are saying. We are not bothered about the chemistry change, the open system stuff and all. If we consider dG equals VdP minus SdT for an ideal gas at constant temperature, we can write dG equals VdP, remove the dt part, and then if it is an ideal gas system, we are going to replace V by nRT by P, the equation of state for ideal gas. Then if we take 1 mole, then we can remove this N as well, dG equals RT by P dP. Now if we integrate it between these pressure changes, some initial pressure to final pressure, that's what we are saying. An ideal gas undergoes a pressure change, P initial to P final. So we can figure out what is the total Gibbs energy change when the pressure changes for an ideal gas of 1 mole, which is RT natural log of P final by P initial. Now this is exactly what has happened on top of the solids in our case. Pressure changes from Pa standard to Pa phi. So we can write that is the Gibbs energy change of A, RT natural log of Pa phi to Pa standard. So this is only the gas in the top of the solids that is undergoing this pressure change, right? So this is indicating Gibbs energy change of A, right? This Gibbs energy change of A is exactly same as what is happening in the solid state because this vapor and solid are in equilibrium, right? So vapor pressure change is now useful to understand change of pure solid A to A in solid solution phi. See, a gas phase phenomena helps us understand what happens in the solid state, right, through the equation of state of ideal gas. That's quite easy for us to use and derive different stuff like this. So that's why we are using that. Now through the same lens of vapor pressure, we will understand chemical potential. This equation we have derived just now, delta G of pure A is RT natural log of Pa phi by Pa standard. This is nothing but RT natural log of activity of A, right? So this ratio is activity of A. Now this delta Ga we can write it as G final minus G initial, Ga bar. We have seen this previously. So activity of only A in the solution is partial. The integral Gibbs energy of A, the integral Gibbs energy of the solution is something else, that is G of phi. but only for A we can put this bar and call it partial molar Gibbs energy of A, and we also told partial molar Gibbs energy is nothing but the chemical potential, right? So we can write this in this form as well. This mu A of phi is chemical potential of A in phi. So now we are connecting, rearranging this slightly, we can connect mu A of phi is connected to activity of A like this. Similarly for mu B we can write this. If you have mu A of phi, mu B of phi, using the rule of mixture we can get the Gibbs energy of the entire solution. Often one mistake that students will do is writing mu of phi, okay, as the weighted average of these two quantities. It is not correct because chemical potential is defined only for each element in a phase and not for the entire phase. Writing mu of a phase is not right. Mu can be there only for individual elements and G can be there for the entire solution. Right. Since we have connected chemical potential of A to activity of A, what we have concluded about activity for phase equilibria applies for chemical potential as well. This is what we have concluded for activity and phase equilibria. Activity of each element must be same in each phase. Therefore, chemical potential also should be like that. If two phases are to be in equilibrium, phi and alpha in this case, chemical potential of each element must be same in each phase. Note what we are not saying. We are not saying mu of A phi is equal to mu B of phi. We are not saying that. Only for A, chemical potential of A is same across the phases. Similarly, chemical potential of B will be same across the phases. So if two phases alpha and phi are in equilibrium, chemical potential of A on this side and this side should be same. These are quite profound conclusions. We will be using them throughout this course. Please keep them in mind. Thank you. I hope the lecture is useful.